Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at our last set of notes from the mole chapter, our seventh set of notes. And today we're going to be looking at an application of empirical formula, which is the formula of a hydrate. Now, a hydrate is an ionic compound that has a specific number of water molecules bound to its atoms. So some ionic substances actually attract and absorb water into the crystalline structure. And when they're full, they absorb a very specific number of water molecules in the hydrate. So that's what a hydrated crystal is. Now, a commercial use of this you may have seen in tennis shoes and electronics equipment, because those little silica packets that say do not eat on them are actually anhydrates. They've had all the water driven off, so that means they can absorb moisture from the air. Well, if you put it in the box with the tennis shoes or with your electronics equipment, any moisture that gets in there, which could potentially cause mildew or to cause rust in the electronics equipment, would get absorbed by that our anhydrous crystal, and it would keep the compartment dry. So what we're actually talking about here is if it absorbed a bunch of water and became fully hydrated, then we would have a hydrated crystal. Now, when we look at the formula of a hydrated crystal, you're going to see the compound. So the formula of the ionic compound is going to be listed, and then a dot, and then a certain number of water molecules. So a couple examples. This is copper 2 sulfate as a hydrated crystal, CuSO4.5H2O, and barium chloride as a hydrated crystal, BaCl2.2H2O. Now, when we name these types of things, what we're going to do is use prefixes to describe those number of water molecules. So copper 2 sulfate pentahydrate. So that would mean 5 waters. Barium chloride dihydrate. That would mean 2 waters. Sodium carbonate decahydrate. That would mean 10 water molecules bound to it. So really the same kind of prefixes we used before when dealing with molecules, we can use here to describe what type of hydrate it is and give a very specific bit of information about the actual number of water molecules that are bound to a formula unit of our ionic compound. Now, hydrate means it's got water absorbed into it, so anhydrous would mean without water. When a hydrate is heated, it's going to drive off the water and the compound is no longer going to be hydrated. If you drive off all the water, then you will be left with an anhydrous substance. The name and formula of the anhydrous compounds would be the exact name and formula of the regular ionic compound that we looked at before. So sodium carbonate without a bunch of water absorbed in it, it's just called sodium carbonate. But sometimes you might see it referred to as anhydrous sodium carbonate. It would be that formula, it just is reminding you without water. Now to find the form of a hydrated crystal, and this is what we're really looking at doing here, we need to recognize it's really a type of empirical formula. The smallest whole number ratio of water to 1 mole of the compound is what's represented by 1 Na2CO3.10H2O. It doesn't say 1, but really it is 1 sodium carbonate. So that's a formula ratio, 1 to 10, that can't be reduced. And the same was true with the copper to sulfate pentahydrate that was listed, it's 1 to 5. Or the barium chloride dihydrate, it's 1 to 2. So it really is a type of empirical formula because your formula unit, there's always going to be one of the ionic compound and some number of water. That's some multiple. It could be 1 or 2 or 3 or 4 or 5. So really what we're trying to do is find the empirical formula. Just like before, we want to get masses, we want to convert them to moles, and then we want to get whole numbers. Now here, the ionic compound is always going to be 1. So if we divide both masses by the ionic, or both number of moles by the ionic compound number of moles, and it will be the smaller of the two or equal to the other one, you're going to get 1 for the ionic compound and 1, 2, 3, 4, 5, 6, whatever for the number of water molecules. And keep in mind, this is kind of like the molecular formula situation. If we do this right, we can't have a half. So we're always going to be double or triple or quadruple. It's going to be some whole number, multiple. Now, in a lab, if we were going to do this, what we'd be doing is using a setup similar you see in the upper right-hand corner here with a Bunsen burner and a crucible with a lid to basically heat up a hydrated crystal. So we're going to start with the hydrated crystal, and we're going to measure it in a crucible with a lid. And don't forget, you always weigh it with a lid, because if you forgot to go weigh the lid with it, your masses are now totally off. And we can't forget, we need to get that from the very beginning. So the first mass we would always need is the mass of the empty crucible and lid. And if the crucible wasn't clean and we were worried about it, you'd clean it out the best you can. But then you need to heat it up to drive off all the water that might be sticking to it, let it cool, and then you would weigh it. So first we need to always get the weight of the empty crucible and lid. Then we're going to put the hydrated crystal inside there, and then we're going to weigh it again. Don't forget the lid. So now we have two masses. And really to finish the lab, all we need is a third mass, and that's it. Now, technically, we could actually figure out the mass of the hydrate if we really wanted to by subtracting these two. But remember, the empirical formula that we were looking at was anhydrate and water. We never really needed the hydrate mass to do that. Now, after you heat it long enough, all the water will be driven off and you'll be left with the anhydrate. Now, in the real world, how do we do that? Well, we would heat it for a while and then we'd let it cool and then we'd go weigh it. But we wouldn't be sure if we'd driven off all the water. So then we put it back on, heat it again for a few minutes, let it cool, and then we go weigh it again. And if the two masses were the same, we know we'd driven off all the water. If they were different, we'd have to heat it up again for a few minutes, let it cool, and then go weigh it. And now if they were the same, then now we know we've driven off all the water. So that's typically what you have to do. And at this point, we'd let it cool, and then we would weigh the crucible and the anhydrate. Now, when you're doing the lab, then you're going to need to get all three masses. You can't forget to do that. We have to have those three masses: the empty crucible, the crucible plus the hydrate, and the crucible plus the anhydrate. And we're going to end up calculating our two important masses from that information. And remember, our important masses are the mass of the anhydrate and the mass of the water. Those are the two masses we need to get. Now, if you think about it, the mass of the anhydrate, if we knew that at the end of the lab we had the crucible and the anhydrate, if we subtract out the crucible's mass, which we found at the beginning, we'd be left with the anhydrate. If we want to find the mass of the water, well, where did we have water? When we have a hydrate. Where did we not have water? When it was an anhydrate. So the difference between those two, and I know the crucible and lid are going to be there as well, but remember, they're there in both cases, so they're just going to subtract out. So the crucible with the hydrate minus the crucible with the anhydrate, that's going to give us the mass of the water. Now, when we go to actually do this, we would get something like this. We would get these three bits of data that we see here. And in order to do the lab, what we'd really have to do is then pull out the important information we just talked about: the mass of the anhydrate, the mass of the water, and then get moles of anhydrate, get moles of water, and then get whole numbers to figure out what that multiple of water was. So how do we go about doing that? Well, number one would be to calculate the two masses we need. The anhydrate, let's say we've got copper sulfate here. So the anhydrate copper sulfate. And then we also need to know the mass of the water. Well, to get the anhydrate, it'd be the crucible lid and anhydrate minus just the crucible and lid. In this case, 12.95 minus 11.36, we've got 1.59 grams of the anhydrate. Now we also need to find the water. Now the water would be the difference between when it was hydrated and when it wasn't. That would be 13.86 minus 12.95. So the difference between those two would be how much water was driven off. In this case, 0.91 grams. Now at this point, sometimes students will do and make the same mistake they made in empirical formula. They will divide by the smaller mass. Well, that's not what we need to do. Formulas are not ratios of masses, they're ratios of moles. So we need to do step two: convert these masses into moles. So we had 1.59 grams of copper sulfate. If you add up the molar mass of the one copper and the one sulfur and the four oxygens, you get 159.6. So our number of moles of copper sulfate would be 0.00996 moles. Then we do the same thing for water. We knew that the water was 0.91 grams of water. If we divide that by water's molar mass, 18.0, we get how many moles of water we've got. So now we know the moles of anhydrate and the moles of water. Now notice the moles of water is bigger. That would make sense because water is some multiple of the anhydrate. Now, the last thing is to calculate at how many water molecules do we really have? Well, if we take the number of moles of water and divide by the number of moles of copper sulfate, we would be predicting or calculating how many moles of water were there for every 1 mole of copper sulfate. Because if I divided both of them by the moles of copper sulfate, the copper sulfate would go to 1, and the number of moles of water in this case would go to 5.0. So that must mean this thing is a pentahydrate. I had 5 moles of water for every 1 mole of copper sulfate. So the ratio of water to copper sulfate is going to give me N. And remember, that's going to precede the water in the formula of the hydrate. So remember, it was some number in front of the water. Well, we just figured out the water number was 5. So that would be our final answer. This is a pentahydrate, CuSO4.5H2O. And don't forget, when you've done the math, don't forget to write it then as a hydrated crystal formula, because that was the purpose, was to figure out this thing. So that's what we really need to do here at the end, is write it out like that. And that's how you go about doing this. And that ends our notes over chapter 10.